project PERSIST, a digital solution in which we have been working for the continuum care of after cancer of cancer survivors. Well, this is part of an activity of dissemination and also part of the external advisory report session that we are celebrating. We have invited we would like to acknowledge our external advisory board members, Clement Fate, a senior consultant at Data Activist, a company that is aiming to make data available. Then Elena Fernandez, who is a visiting associate professor at the University of Minho. And finally, Guillermo Del Fiol, who is a professor and vice chair for research of the Department of Biomedical Informatics at the University of Utah. So thank all of you for joining, and I will start with a short introduction to the PERSIST project. As I mentioned before, we are targeting epidemiological challenge in our society, which is the increasing number of people who are survivors of cancer. As you may know, the incidence of cancer is increasing. The number of cases that are diagnosed in Europe is increasing every year. And also the survival rate. We have better tools to diagnose and treat cancer, and the survival rate, luckily, is increasing as well. This is increasing, and the number of cancer survivor population is increasing, is growing, and they have very specific needs that require long-term and personalized care. And this is obviously putting pressure on the healthcare system because it hasn't been designed to meet the needs of those patients. So we identified this issue and we created a partnership. We applied for a Horizon 2020 project, research and innovation action, in which we created this consortium of 13 partners from 10 countries all over Europe. And yeah, it includes big medtech companies such as Dedalus, for instance, also SMEs, hospitals, research centers, also the university, academia is involved as well. And finally, also national patients organizations, such as the one from Bulgaria, who is participating in this project. At a glance, this is what we are proposing in PERSIST. It's a new healthcare model that addresses the challenges of patients and healthcare professionals regarding cancer survivorship. For professionals, we identified that the main challenges are related to the poor coordination between different care levels. We have very good oncologists in Europe who are able to treat and to diagnose cancer, and they are experts in the field, obviously. But this knowledge that they have is not shared with the other care levels who are also involved in the treatment and follow-up of cancer survivors in primary care, for instance. Also, there are not individualized care plans. There are some plans for cancer survivors that are targeting maybe some types of cancer, but are not individualized per patient. And this is, it provokes that the needs of each individual are not met. And there is a lack of specialists. As I mentioned before, the number of cancer survivors is increasing, the population is growing, and there are not enough oncologists to treat and manage those patients with the standards they require. For patients, the main challenges are associated with toxicity because they have undergone treatments which are really hard, like for instance chemotherapy, and that have side effects and after effects. They have an impact in their life, which is they cannot recover the lifestyle after they have overcome the primary cancer diagnosis. And they cannot, for instance, come back to their work, and they cannot. This is also triggering some financial problems, and they cannot recover the lifestyle, the social activation that they had before the diagnosis of cancer. And this is obviously affecting their psychological status, their emotional status, because they have fear to recurrence. First of all, they cannot recover the lifestyle, and moreover, in some cases they have undergone changes in their bodies, like the removal of a breast, or in case of the colorectal cancer, also sometimes they have to wear a stoma, and that's impacting their lifestyle and their emotional status in a deep way. What we propose is a new healthcare model with three pillars, based on three pillars. First of all, data capture for from different sources, then intelligence, and finally decision support. Regarding data capture, in our project, we are capturing data from different sources, from the electronic health records from 4 hospitals in Spain, in Belgium, in Latvia, and Slovenia. Also, we have developed a mHealth application. Later, we will show you it with more detail. But basically, the mHealth application is able to collect information coming from a smartwatch, that a smartband that can collect vital signs such as the heart rate, the blood pressure, also a step count and sleeping patterns. Apart in the mHealth app, patients can also record some video diaries, taking advantage of a conversational chatbot that is making questions. This information, these videos, are later analyzed in order to identify patterns of depression, signs of depression and emotional stress in those patients. And also they can fill prompts and prems using some questionnaires through the application. Another source of data is the images that we are capturing from the laboratory, from liquid biopsy. And what we are targeting and addressing is trying to identify and classify circulating tumor cells of patients. In the second pillar, we are working in intelligence. We have built a big data and artificial intelligence platform, taking advantage of some standards, in particular for communication, such as HL7 FHIR standard, and also some other standards for terminology, such as SNOMED and LOINC. And we have been this platform in which different artificial intelligence services run. And in particular, we have developed artificial intelligence models for the automatic with deep learning algorithms in order to count the CTCs in the liquid biopsy with the images from the histopathology laboratory. Also, some artificial intelligence models to predict the risk for recurrence, to predict the trajectories of patients for different clinical outcomes, and also some algorithms, some artificial intelligence algorithms that are able to analyze the video, analyze the speech of the video recordings of the diaries that they are recording, and is able to identify these signs of depression or emotional stress. And finally, we have the last pillar, which is the decision support. We have developed a clinician application in which the professionals who are in charge of the follow-up of the cancer survivors can see the trends of the patients and can receive also some alarms when some adverse event or risk for an adverse event is detected. So this is the healthcare model behind and supported by the technologies that we have developed in PERSIST. We are running a clinical study with 4 clinical centers, as I mentioned before, 2 types of cancer, breast cancer and colorectal cancer. We focus in these 2 types of cancer because they are 2 of the most prevalent cancer types in Europe, and also because they have a remarkable impact in the emotional status of the patient. We mentioned before why, the changes in the body and the fear for recurrence. Then we have 160 patients involved in 2 subgroups, one that have undergone chemotherapy and one that haven't undergone chemotherapy. The study is designed as a single case experimental prospective study with a 6-month follow-up, and each patient is its own control group. So we are comparing the pre and post intervention status of the patient. The study, well, the design of the study started at the beginning of the project, in which we were training the physicians in the use of technology, in the protocol of the study as well. Then we started recruiting the patients in the 4 clinical centers, 4 hospitals. Then we carried out the first part of the study, in which we were working in data collection and usability. We were co-creating the technology with users, and this is relevant because it allowed us to adapt to them and understand which were their needs in terms of interaction, in terms of digital literacy. And finally, we are running right now the full clinical validation of the intervention. It's a 6-month follow-up, as I mentioned before, and it's expected to finish by the end of December. Then the project will last until February we will have time to analyze all the outcomes of the study. Also, we will be working the exploitation of the results that we have generated, but the clinical study will be finished by the end of December. So the intervention consisted basically in the usage of the mHealth application. I have already mentioned that we'll go later more in depth into the different variables that are collected, the different analyses that are performed, and also the clinical decision support system for physicians. So they can have a better picture of the patient, they can personalize treatment and enable a better follow-up and management of each single case and each patient. The dimensions that we are measuring in the clinical study are the usability, user experience, acceptability, self-efficacy, which is the main outcome indeed, the empowerment of the patient, quality of life, the health status of the patient, obviously, although we want to see what's the real impact, and in such a short time, it's not easy because it's just 6 months, and cancer survivors longer follow-up, maybe it will be more interesting to understand which is the real impact in the health status, and also the healthy habits of the subjects. Okay, and our main hypothesis is that the participants in the study will be able to increase their self-efficacy and using this personalized intervention. And that's all. This is a very short introduction. Obviously, the project has been a 3-year project. Many things have happened, but this is just a snapshot, a glance of the project. And I'm gonna give the floor back to Isidore, who is gonna present the mHealth application. Isidore is a researcher from the University of Maribor. Well, Isidore, the floor is yours. Please tell us about the mHealth application.
Yeah, thank you, Alberto, for the introduction. Can you please move to the next slide? So this slide actually highlights what the PERSIST project is about. Our main objectives are, in principle, first to empower patients, cancer survivors, and the second one is actually to personalize cancer survivorship. So overall, to improve their quality of life and well-being as much as possible. So how do we achieve this? Well, in general, by exploiting the information hidden in clinical data, in big data repositories, and aggregating this information with the real-world data, which we collect from everyday experiences of patients that they actually experience at home. So our mHealth app focuses on giving patients some information about their well-being, about their status, about their guidance even, but also it serves the purpose of collecting data. As you see on the image, we collect this data in several ways. One way is through standardized questionnaires, prems and proms, as Alberto already mentioned. The other aspect are CTCs, liquid biopsy, where patients actually donate blood, which is explored. The third one is the smart band, basically an IoT device, which can collect some, let's say, physiological parameters, such as heart rate, blood pressure, sleep patterns, and activity. And finally, diaries, where diaries actually represent the biggest innovation of PERSIST in terms of real-world data collection. Non-clinical real-world data collection, because the other major innovation, of course, are the CTCs, the circulating tumor cells, where we want to. So in this non-clinical data collection, we want actually to collect non-cancer-related symptoms. So prems and proms are very specific; they are very disease-centric, whereas patients, especially cancer survivors, often experience other symptoms which are non-disease related, and if we don't know about them, we don't ask or propose them to be answered through questionnaires. However, through diary recordings, patients subconsciously can mention some issues which we can detect through, as Alberto mentioned, our mRAST framework, which focuses on speech features, on language features, and on, let's say, facial features in order to classify not only symptoms of psychological distress, but also to extract some possible symptoms for other diseases mentioned in the discourse. Can you please move to the next slide? So this is an example of our basically mHealth app for collecting real-world data. As you see here, we have a smart band, we have an emotion wheel for which patients express how they feel, and we also have questionnaires as well as the diaries, and of course the CTCs. So ideally, the routine of a patient's routine of collecting this data is triggered by sort of our clinical decision support system through a care workflow plan, for which each clinician can specify which kind of activity the patient is asked to do at certain times of the day, at certain times of the week, and the system can then automatically trigger the activities through notifications. So in this functional diagram here, we actually somehow highlight what is done through the diary recordings, but we also have a demonstration. So maybe you can jump into the next slide, Alberto, which actually represents a couple of interfaces that we have. So what patient can actually see, in addition to the interfaces related to tasks we request from them, they can also get some information about cancer. We build or survivorship itself, some clinically validated advice through our knowledge base, and of course some information related to the data they have collected, because one of the most important aspects of patient empowerment is actually giving them feedback information. And this is what actually PERSIST application is all about, the first objective, the empowerment. Maybe move to the next slide and we can just provide the demonstration here. This is an actual recording of the use of the mHealth app. It's a YouTube recording. I don't know, it's really slow on my end. So this is, when the patient enters the application, we have an embodied conversational agent to actually, somehow make this more personal. Then there's a summary of data the patients can see. So we demonstrate also how they measure the heart rate and the vitals. It is measured. It can be done either manually or via smart band, because some patients actually have their own smart bands which are not integrated. So we also support them to manually insert the data. But ideally, if the app is the device is integrated, it will do it automatically. It also can be used for direct interaction with clinicians or healthcare professionals. And this is the diary recording part, where we ask patients to just record short, 1 to 2 minute videos where they express a couple of sentences about their experiences in their daily lives. And this is some information. This is the knowledge base that I was talking about before. So this is an example of how a patient answers the questionnaire. The questionnaire is actually chatbot driven. So it is generated automatically and then stored as a FHIR resource questionnaire response. Now the emotion wheel. We had some troubles with designing the emotion wheel. It used to be a wheel. However, then after several sessions and let's say discussions with patients themselves, we kind of added, simplified, changed things, because the psychological notion of emotion is sometimes not really well understood by the patients. And this is also reflected in actually prems and proms. So this was our let's say mHealth application. You can move to the next slide. And that is why we said, okay, because often prems and proms are not understood, people don't really know how they feel. Why don't we collect information for diaries? So that's why in PERSIST, we actually designed a pipeline that can extract and collect real-world data from patient diaries. So the first three pipelines are primarily dedicated towards the text feature extraction pipeline, the audio feature extraction pipeline, and the facial feature extraction pipeline are primarily dedicated to detecting psychological distress, basically symptoms of depression, where we classify the video recording as at risk for depression, as well as enhance it with observable features, which can actually provide additional required context for the clinicians to see whether the AI was sort of right or wrong and explain the AI decisions. So instead of post hoc explainability of deeply trained models, we actually provide observable features which are generated based on the theoretical background of how people with depression express themselves. And the final fourth pipeline, it's for symptom extraction. This one actually exploits the ontology of Symptoma, the partner in this project, and it extracts possible causes and symptoms from the text being spoken within the recordings. Of course, in order to facilitate this pipeline, we need speech recognition engine. So for PERSIST project, we actually deployed our UM's proprietary technology, which supports 6 PERSIST languages: English, French, Spanish, Latvian, Russian, and Slovenian. Of course, if we have other resources to support other languages, but at this point, these were the necessary languages. And this feature is, as it will be shown in the next slide, is completely end-to-end. So after the patient records it, we can either manually or automatically, you can play the video, trigger this process, and the video is correctly annotated. So this is the demo of the full pipeline. So this is an mHealth app part where, of course, we have unclassified diary recordings, and the clinician can actually click and request for the analysis. This is the backend part. It won't be long because it's only windows that are popped out. So no person actually sees the video itself or knows what is actually in the video. And the process is, as you see, fully automatic, and the end result is then basically represented like this. So these are the possible. This is the no detected risk of depression, and then a list of possible symptoms and causes. So this is one aspect of PERSIST. Now the next aspect of PERSIST actually deals with specifically with collecting real-world data with a personalized chat. So, okay, we thought, what if we detect some symptoms? If there are some alerts triggered by the clinical decision support system, it would be great if we can somehow do, let's say, a post detection survey to see or facilitate what these symptoms could represent. To this end, we provide another pipeline, which again is based on Symptoma's REST API chatbot, which drives a, let's say, disease, we call it disease-centric discourse, to investigate what a specific symptom, such as fever, would be all about. And the next presentation, in the next slide, showcases this fully end-to-end pipeline. So this is how it is represented to the patient via a notification. And yes, then you see it's only yes, no, or I don't know questions about specific symptoms. This is it. The patient filled in the questionnaire, We will now show you a bit of backend. Again, it's fully automated. Everything is just as you see command windows. Nobody looks at the text or nothing. This is what happens, when we communicate between the mHealth app and the Symptomas backend. And then we store this information as file resource, which as file composition, which can be easily shown to the clinicians in the clinical application. So this is the discourse, as you see, and also down there are possible causes and, possible causes, yes. And then based on these informations, either clinicians or even an AI can better decide how to refine, let's say, the regular survivorship routine. And with this demonstration, I would finish with the, let's say, data collection and patient engagement part, and I would give the floor to Tunç from Emoda to start discussing the clinical application, the mClinician app, and the clinical side of this. Thank you.
Yeah, thank you, Isidore. Hope you hear my voice well. In PERSIST, we have lots of data coming from the sensor network and the mHealth app and other outputs of the AI, as Isidore mentioned. And now we can use this data in order to support the clinicians. The idea of clinical applications is supporting the clinical parties, and we have this UI in web that it makes it easy to create patients, use their enter their login and login passwords, and also all the details about their prospective clinical data. Let's say mostly specialized on cancer patients. We can see their treatments here. You can ingest their treatments, tests, and all other diagnoses and symptoms related to patient. That fits that fits the CDSS and trajectory analysis and the outputs that we show to the clinicians. We can go to the next slide. I will show you also the clinician application. We have this clinician application. It's a mobile app. That's easy for clinicians to see anywhere, anytime about the data collected in PERSIST about the patients. Also the CDSS outputs that are constantly supporting clinicians with the data derived from the system. So we can display the patients here. We can receive the alerts raised in the system with notifications, and also as the showed earlier, they can handle the active alerts of the patients by initiating CTC or taking another action according to the alert context. And also they can see patients' heart rate, blood pressure, activity trends, and also the outputs of trajectories and where this patient lies on these trajectories. So I will show you a quick demo of the mobile application. Yes, mClinician mobile application. We can see the clinicians can just enter with their credentials, and they can see the patient lists and the details of the patient. Just easy by tapping on the patient ID and they can see the patient-related data here, like alerts, trends, diary analysis, and CTC results. Also, if there's an active alerts of patients, they can just see this on top of the patient's info page. Here are the alerts of patients. Also, after an alert is handled some way, they can just archive it and access it anytime to see what the system brought to the patient in history. So also they can easily access all active alerts in all patients easily from the application to just engage with the treatments and to decide what to react with this alert. Also, they can see the appointments of the patients here through this application. Yes. And also the trajectories are with the collected data. There are types of parameters here for each cancer type in the project. We can see the trajectories trained and with the retrospective data, and also with ongoing with the project, the prospective data also used here to retrain the system and give recent outputs with the current data in the system. In the patient detail, we can see active alerts. As it was shown earlier, this is the CT part. Here, the alert is caused by a patient responding a question with pain, and so the clinician can decide here to initiate this disease-centric discourse to gather more information about this pain. It's the outputs of the conversation between Symptomas API and the mHealth, and it's collected as in mHealth application and answered by the patient. The results of this detailed conversation are also stored in the server related to this alert, and after this process, the clinician receives a notification and checks back what the patient further give back to the system about this alert station, maybe pain or another symptom, and this API results with the detailed information on the alert. Symptoms and possible symptoms that will cause this pain in this case, or any other alert context. Here we see this. We see the result of DCD. What patient answered and what possible causes the system give us as outputs according to this alert, which patient had some pain. Also, these alerts are after then archived in the system, and so they are not always displayed to the patient, to the clinician. Also, the clinician can access to patient trends. Trends are the data collected through the smart bands, the activities, steps taken, and the heart rates and blood pressure. They can be displayed in some different time periods, like 7 days, 30 days, and 3 months. And also they can just go through the values in this time frame. As you can see, there can be other time frames to show the condition. And also the 3-month time frame for the same data. And here we have this diary analysis. We'll show the results. They can access in time to the diary analysis. If they are already finished, they can display the results of the diary analysis as symptoms, and also some text from the diary itself to further investigate the patient. We have CTC results. When a CTC result is recorded, the clinician gets a notification. They can see the analysis report. Here we have this. Actually, if it's a report, it's there in the PDF, and also the observations gathered from this CTC. Also, we have the CDS, clinical decision support services, working behind to raise alerts, as well as some summary about the cardiovascular risk disease, colon cancer recurrence risk assessments. Here we are using the high risk markers gathered from the trajectory results and the literatures about colon cancer and related diseases. We are summarizing to the clinician with the recent related data about that topic. Also, they can access the trajectories and where this patient actually lies in these trajectories. Also, we have this recurrence prediction will be detailed explained later. As far as I know, it gives a percentage of recurrence possibility. That's pretty much it, the application.
Okay, thank you, Tunç,
Yeah.
for the presentation and introduction to the mClinician application. So now I'm giving the floor to Shaila Calvo, who is also a researcher and engineer at Gradient, and will present the circulating tumor cells automatic count algorithms that we have developed in PERSIST. Shaila, are you there? We cannot hear you. Well, some technical problems. So maybe we can move forward to the other presentation that we have, which is the recurrence prediction side. Like you can connect later. We will get back to the CTC counting. So Elena is going to present Elena Campillo, who is also a researcher and engineer for Gradient, is going to present the recurrence prediction algorithms that we have developed also in PERSIST. So Elena, are you there?
Yes, can you hear me?
Yeah, we can hear you.
Great. Okay, so we have just seen the mHealth presentation, and in there we saw what was a recurrence prediction for cancer. So one of the things that is a real problem for people who suffer from cancer is that sometimes even when they are cured, they can have a relapse, then they can get cancer again. And given all the data that we have and is stored in the PERSIST Fire server, we wanted to develop a machine learning model that could predict whether a patient with the data that we have would have suffered from a relapse within 5 years. So we developed two different models. One for colon cancer, for colorectal cancer, and another one for breast cancer. And they predict the probability that a patient will suffer from a relapse. Can you move to the next slide, please? So in order to train the models, we used the prospective data that was in the Fire server. That is the data of the patients that were collected before the start of the study. And we used the data from the patients from Chudelig. In total, there were more than 4,000 patients with either breast cancer or colon cancer. And the characteristics that these patients had to have in order to form this data set to train the model was that they had actual data in the Fire server, that they were still alive 5 years after their initial diagnosis, and that they had a valid breast or colon cancer diagnosis in the server. So the data that we used to train the model was, it's divided in 3 parts. First, there's like general data that was used to train both models. And then there were special data selected just for breast cancer and just for colon cancer. So the general data was data like gender, BMI, smoking or drinking behavior, what were the tumor characteristics, some hormone markers, when was their earliest diagnosis, when was their newest diagnosis, the number of surgeries they went through, how many radiotherapy sessions or chemotherapy sessions they went through. And then for breast cancer, for example, we used hypertension, diabetes, obesity, etc. And for colon cancer, we used comorbidities such as arrhythmia, valvular disease, hypertension, diabetes again, renal failure, weight loss, obesity, etc. Next slide, please. So once we had the data, the training data selected, we used that data to train 5 different models, 5 for colon cancer and 5 for breast cancer. These models were a deep neural network, a XG boosting, a gradient boosting, decision tree, and logistic regression. And after training these models, we chose the one with the best performance, which was gradient boosting in the case of colon cancer and XG boosting in the case of breast cancer. I will talk a little bit more about this in a minute. But first, we trained the models with a holdout strategy, which means that 90% of the data was used for training and another 10% was used to validate the models and make sure that they learned correctly and could perform well in media data. So the measurements that we can see in those tables are for this 10% of final testing. In order to train the models, we used k-fold cross-validation with a k of 6, meaning that for each iteration, we used 75% of the training data to train the model, and 15% was used for validation in each one of those cross-validation passes. And we also did some hyperparameter tuning using grid search in order to optimize the performance of the models and obtain the best one possible. So we can see here that in the case of colon cancer, we obtained for the best model an F1 weighted of 0.78. And for breast cancer, which performed much better, an F1 of 0.9. Next slide, please. So once we had the models, we developed a service, a REST API service, that the mClinician application could connect to. As we can see in this diagram, the recurrent service architecture diagram, the CTCs in this case is the mClinician, sorry. And the mClinician can make requests for a patient and a type of cancer. And our service makes a query to the FHIR server to obtain the data needed to calculate that prediction, and then it sends that data to the respective model, depending on either if it is breast or colon cancer. And this model gets a prediction, and then it sends that prediction back to the mClinician app. And just the last slide now. And how the service gives back the prediction is a JSON object, as we can see here. It looks very complicated, but the important part is the value, which in this case, in this example, would be a prediction of 27% probability of recurrence. And that's it for this part of the presentation. Thank you very much.
Okay, thank you, Elena. So we are going back to the circulating tumor cells automatic count algorithms. Shai, I think you have resolved your technical problems.
Hello.
Yeah, we can hear you now. Perfect.
Perfect. So sorry, everybody, I have technical problems. So now we are going to talk about the circulating tumor cells counting system developed here in PERSIST. Circulating tumor cells are cells that detach directly from a primary tumor and then go on circulate on the bloodstream so they can colonize other tissues and cause metastasis. So we can move. Perfect. In order to analyze these CTCs, we have developed a CTCs counting system, which is the one you can see here in this slide. This system consists in two different flows, one from automatic counting and another one from manual validation. And both of these flows have a common start, which consists on the extraction of some microscope images in order to be analyzed and detect the different CTCs. And starting with the manual validation, here it is the experts who analyze the microscope images and detect the different CTCs. And then they can add this information into a CTC web application that we are going to see in the next slides. And this information can be then sent to the PERSIST file server in order to be used or analyzed from other PERSIST modules like the mClinician. And in order to help these the experts work, and which can sometimes be very hard and time consuming, we have had another flow, which is the automatic counting flow, where users can upload the different microscope images into the same web application, and then these images are sent to a deep learning algorithm, which is able to analyze the image and predict where the CTCs can be. Then this information is returned to the CTC web application, where the experts can analyze the results. So in the next slide, thank you, we can see how the automatic counting works. Here we have some screenshots of the CTC web application. So in the first screenshot, we have the screen where users can upload the different microscope images. And then if we click in the upload image, we send this information to the artificial intelligence, and in this case, the deep learning model, in order to analyze these images. When the model finishes its works, it returns a prediction ID. This ID is shown to the user in the screen, but it is also sent to the email in order to keep that information. And then we go to another of the screens of the application, which is the one you can see in the bottom of the slides. And then we can type this ID and retrieve the deep learning model prediction. So here in the last screen, you can see a result of one of the images we have. Here the model have detected one CTC, and we display this information to the user divided in the different layers of the image in order to be more useful to analyze the CTC results. Here we can also add two different sliders in order to play with the brightness and also to apply a color filter in order to make it more easy the analysis. So we can move forward, and here we want to talk a little bit about the deep learning algorithm. We use specifically convolutional neural networks, which are networks which takes an image as input, and they make some convolution and pooling, which are mathematical operations, in order to extract the relevant information and can make the different predictions. We have tested different convolutional neural networks architectures, and finally we made a evaluation of the different results, and we select the three best results, which are the ones you can see here in this table. And because of the relevance of having false negatives, talking about the cancer detection, we have tried to maximize the recall over the precision. So finally, we select as the best model the one of the bottom of the table, which is a detector-less architecture, which gives us a 72% approach of precision and an 87% of recall. Here, also in the bottom of the slides, we present you some different scenarios and which is the performance of this model. We paint the ground truth CTCs in green and the artificial intelligence detections in red. So here you can see that the 3 CTCs are correctly detected, but we have also some false negatives and which are very, very few, but we have some of them. And also we can have some false positives, which are then analyzed in the web application by the experts. And thank you. Here, now we are going to talk about the manual validation, which is the other flow of the application. In this flow, it is the experts who add the information to the application. And here in this slide, you can see how the information is presented to the user. So here in this screen, the user can type the patient ID, and then the different CTC reports are shown to the user. Here also the expert can modify, delete, and also add some new diagnostic reports regarding to CTCs. And in the right side of the slides, you can see which is the information the application can allow us to add. This information consists of the different type of CTCs, also to select the cancer type between breast and colon, and also we can add different images and also a PDF report on a brief description in order to send all this information to the file server, and then can be used in this application and also in the other PERSIST models. And that's all from my side.
Okay, thank you, Shaila. So, well, with this last presentation, we have covered the whole, well, all the parts of the project that we wanted to showcase today in this webinar. I would like to end the presentation and the webinar just with a reflection on which is the added value of PERSIST. Now that we are getting closer to the end of the project. Basically, I think that the added value and the main outcomes of the projects are the better understanding of the cancer survivor, because this is somehow unknown, especially for technologies, for people who are developing technology, healthcare technology, which is not adapted to them. And I think we have learned a lot from those bases and in this field. Also, the reference and guidelines for survivors that we have created that could be used in order to shape and to engineer the healthcare system of the future with these tools supporting the healthcare model, the PERSIST healthcare model. Also, the development and validation of new technology tools that were not available in the market and that can have an impact in healthcare and also in the healthcare industry in Europe, such as the interoperable and scalable data platform that we built, also the artificial intelligence model that have been presented. Also the Ruby chip, we haven't mentioned it, but one of the partners, Ruby Nanomed, have developed a chip, a device that is able to isolate the CTCs, and this was really important in order to be able to produce a valuable biomarker who can be incorporated in the follow-up, in the prognosis of patients, and all the application and interaction models that you have observed that we have been refining in this co-creation process and that are supporting the healthcare model that we would like to implement. The patient engagement and empowerment were very important. They were engaged from the very beginning of the project in the co-creation of the technology, and this was really important in order to ensure the acceptability and adoption of the technology, and that we are meeting actually their needs. Also, the ecosystem that we have built in the consortium of large companies, SMEs, healthcare organizations, research partners, and academia that have been working together and that have produced some results that otherwise wouldn't have been achievable. And finally, the exploitation of the results. This project is oriented to the market, to the industry, and we are working currently in this analysis of the results that we have generated and how we can transfer the technology to the market and build a business plan, because the business model is not clear sometimes for artificial intelligence and for such specific application like the one we are addressing in PERSIST. So that's all from our side. Here you have some links to our channels, to our social media, where you can learn and follow the project. We are getting closer to the end, but still, I'm sure that we will create some content which might be of your interest. And yeah, that's all. I don't know if we have much time for Q&A, but if there is any hot question that we can reply, please don't hesitate. Now is the moment for that. From the audience or from other, I know there are some members of the consortium as well in the call. So if someone has some reflection, otherwise you can contact us in our social media or by email, on LinkedIn or whatever, and we will be more than happy to reply to your questions or any doubt that you may have about the project and anything you want to learn about our technology. Okay, so that's all. Thanks for your attention. Now we're going to move to I think we can stop the recording.